I'll say this. So we will try to do what is called the radical axis. This is just the next thing after your power of point and so on. This is the radical axis, and we will do the radical axis theorem, which is sort of a different way to show concurrency from what you may have done so far. Okay, right. So I think it's very simple. Otherwise, we'll take the help of the internet or some book. So we have two circles. Okay. We have talked about this. It has been the highlight for us is the power of point. Okay. So given a point, point P, you look at the power of point of P with respect to this circle, and you can look at the power of P with respect to the second circle. Okay. So that we know what that is, and we know simply that it is just the square of the length of the tangent. That is the power of the point P with respect to omega 1, with respect to gamma 1. It is obviously equal to all those other things. I mean, you understand that, but this is, we are interested in those points P. So we are interested in this set P such that power of P with respect to gamma 1 is equal to power of P with respect to gamma 2. It means nothing. It's a very simple thing. It just means that the length of tangent from P to gamma 1 is equal to the length of the tangent from P to gamma 2. That's all I'm saying. It's nothing complicated. Right? We are interested in these points. Okay, are you understanding what I mean? There can be many such points, right? Can you give an example of such a point? Can you give an example of an example from this set? You could say, look, this point is not equal, but can you give a natural example where uh, which you know that the length of the tangents will be equal? And this is a very simple example. And now lots of homework is coming, okay? So you have to do them. I'm saying that you just take the common tangent. You know that there is a common tangent. Right? You can draw, you can find its length. They are basic calculus. These are just basic NCERT circle geometry thing. If you have not read them, don't panic. Take them, try them. If not, you get the time, then you read it later on. Okay. But obviously we cannot cover everything in details here. So you take the common tangent, okay, and then you take the midpoint. As simple as that. Right? Take the common tangent, take the midpoint. This is certainly his work, right? This point P will also be in the set. Okay. Now the collection of all these points, how does it look? What shape does it form? If these circles were points, then how would it look? Then I'm just asking for what I'm talking about is the perpendicular bisector, am I not? Right? Then I'm just asking for distance from this point to this circle, which is a point. So it just becomes the distance between those 2 points. Right? A circle with radius 0. Right? Then I'm just asking for the angle for the perpendicular bisector, which is probably the first construction you do, right, in geometry. This is a generalization of that when those points grow large. Okay, and then yeah. So again, and this is what mathematics is, right? Generalizes, right? It generalizes to a more general truth that it is again a line. Set of all these points, which at the beginning may look like a complicated set, but it is just a line. I'm not proving it right now. Not proving it. Proof is not difficult, but we will do it at some point if needed. We will certainly do it. But just assume that it forms a line. Okay. Okay. I'm not even asking you to prove this. Okay. Just assume it forms a line. So this line is called the radical axis of these two circles. So it's an axis which is really important. It's a line, it's an axis, it's a line. It's an important line. Now what is the thing? Now in the picture come three circles. Okay, it will be perpendicular to this two centers. That's not surprising. It won't be the midpoint. That is probably clear. Big, very small circle. It will not be the midpoint. Those ratios, all those calculations can be done. They are easy. But we will do them at some point. Now the point is that let's erase this and let's say this is the radical axis. Okay. Now three circles. When three circles come in, for four circles, it does not work, and actually is a very interesting thing because 3 choose 2 is 3, but 4 choose 2 is not 4, and things like that, right? It's not like it's not aligned in any way. It's just randomly third circle comes in the picture. Then what happens is that again you draw the radical axis, right? Of this two, let's say of these two you draw the radical axis, right? Again it will be line. And you know what I'm going to say. Again, gamma 2 and gamma 3, you draw the radical axis, it will be a line. But those three lines will pass through a common point. Boom. That's a very nice result. Okay. So you understand what these lines are, right? This line is L1, 1, comma 2, which is it's the radical axis of 1 and 2, gamma 1 and gamma 2. And this gamma 1, gamma 3 ka radical axis is probably R should have been 2, 1, comma 3. They actually pass through a common point. Okay. The proof is, I suppose, very simple. Why? Because you forget the third one, just take the first two. Okay. And let's say that they pass through this point. Okay. Now you have to so what do you know? What do you know about this point? Let's call this point P. Let's forget this point. Okay. So just come back and just see that there are three circles. I've drawn one line, L1 comma L, this is the one line, L1 comma 2. That's radical axis of gamma 1 and gamma 2, and L1 comma 3, that's radical axis of gamma 1 and gamma 3. Let us just, we can even forget the radical axis thing. What I'm just saying is that when you draw the tangent from here to here, okay, this length of this tangent is equal to length of this tangent. That is all I'm saying. Why? Because the point P is on L1 comma 3, right? So power of point P with respect to 1 and 3 are equal. So length of the tangents. I mean, obviously, if you draw a tangent from here to gamma 1, that obviously has the same length. That is always true, right? But gamma 3 also, they have the same length. That's courtesy because P is on L1 comma 3. Now you do the same thing because P is also on L1 comma 2. And so this tangent, this length will also be equal to this length. That's it, right? So what does it mean? It means that from this point P, when you draw the tangent to the three circles, they all have the same length, right? What does it mean? It means that the point P is on the radical, so point P, right? So point P, x1, x2. So what have we said? Px1 this is equal to this. This is what we have got. Okay, what does that mean? It means that P is on the radical axis of gamma 2 and gamma 3. So whatever the radical axis is, it will pass through these 2 points. That's it. That's all I'm saying. That the radical axis is the three of them are. So it means that the three of them are concurrent, right? Because that point has to be on the third one also. That's all it means. Okay. So is it fine so far?
Yes.
Yep. Now let me,
Yes.
right? So that's good. But actually we won't need this much. We just need this. Let me ask you this, and this probably I also gave for a homework few days back, few classes back. When you have three circles, okay, let's forget the third circle. What's the radical axis of these two circles? Is a common tangent, right? Because obviously, yeah, it is a common tangent. So this tangent length is equal to this tangent length because this is tangent, and then this is so, and but because it's a line, that has to be proved, right? Obviously, in this case it is clear that it will be a line, right? Because if you take some other point and you take this tangent length and you take this length, you can probably some easy calculation you can show they are not equal. Okay, but that's okay. We need this thing. And then what I had asked you people to show was a very special case of this radical axis theorem. I asked you to show that the three, and this is probably an exercise in RD Sharma or something, some very any book probably, is that these three lines are concurrent. Very basic exercise. You can easily prove it. We have basically proved that today in a more general way. Okay. Okay. Now tell me if so. We don't need this also actually. We need this case when the circles are concurrent. Intersect. Now what is the radical axis? Right? It will be the common chord. Probably not completely. Is it obvious that it's a common chord? Mm, yeah, right. Because I mean, because this point, the power of point for this, because this point P has power 0 with respect to both the circles. And this point P also has power 0 with this point Q also has power 0 with respect to both the circles, right? And so these 2 points are on the radical axis, but the radical axis is a line. So it has to be this line. This proof is very simple, right? If you think simply like this, that it can also be 0. For a point, if point is on a circle, then the power of that point with respect to that circle is obviously 0. And it's on both the circles. That's it. So it's that line. As simple as that. This is what we need. This was the situation which we had, right? It was a situation where you had three circles, and this is like looks like a miracle in this special case, but the way we have talked about it, it's not a miracle, right? That all the three chords will actually be concurrent. That's it. That's the game. Okay, we have proved it. So meeting is going to end, and we'll move on next. We'll try one more problem at least. At least. Okay. Let's see. So I'm ending the meeting. Just have a look at it.